Hey future engineers, welcome to the channel where learning is fun, where formula meets tricks and stress meets strategy. Today we are cracking down another very important chapter of our syllabus, which is relation and function. Okay, this is again the first chapter that we are discussing in Sankalp CET 2026 batch. Okay, one of the very important batch that has been launched for sole purpose of helping you out to achieve great ranks in CET in KCET 2026. Okay, so I hope this is very clear. Now, so why we are here with this particular chapter? First of all, it's a very simple chapter. It's a very straightforward chapter. Okay, the questions also are very much straightforward in this examination. Okay, and high weightage for both PU2 and CET, which is our goal, right? So let's see the planner of the chapter right now, and then we'll move on to our session. So first thing that we have over here, if you look at the chapter planner, so first thing is we're gonna do it in 4 parts. The entire chapter will be covered in 4 parts. So we'll have total 4 videos for this chapter. Part 1 will be types of relations. Okay, part 2 would be types of functions. Okay, and in part 3 we'll deal with KCET PYQs, and part 4 will be JEE Mains PYQs. Okay, so this is the structure of your Sankalp 2026 batch, where we talk about the first segment is concept sessions, the second segment is the CET PYQs, and the third segment is JEE Mains PYQs. Okay, so I hope this is very clear. Now, why are we doing all of this, sir? Because we have a goal of, set for ourselves. We want a very good college in our in our preparation journey for our engineering. Okay, so for that, and why we are doing all of that? Because we have a story to tell, and the story is our greatest result for KCET 2025 batch. You can see the results over here: 171 rank, 443, 693, 752, 934, 1197, 2043, all the way till 5534. I have not taken all the names over here, but you can see Prajwal is there, Kiran is there, Diksha, Samiksha, Sachin, and Harshit, Chinmaya, Tanmay, all the way till Gagan. Okay, so we had not only these many names, there were much more names with such a good rank, but not able to display right now. But if you have watched our session, you'll know, okay, yes, the results we showed in one particular session. So our goal for this this series, the Sankalp batch, is to make you one of the toppers, and your name, your picture should be over here in the results video of KCET 2026. That's our clear goal. Okay, and this video is gonna make you few steps closer to that particular goal of your dream college. Okay, so let's see. This is our result that we had, and this is our goal. This is the task that I'm assigning to you. If you follow us properly, if you are able to follow our instructions, do all the work, of course, believe me, you will be among the rankers next year. Okay, now if we look at the chapter insights, what we have to know about the chapter before starting it, the first thing is very clear. This chapter is a foundation for topics like calculus. Is it, sir? Yes, of course. When we talk about functions, right, whether the functions are trigonometric functions, whether they are modulus functions where we break them into continuity and differentiability questions, yes, they all play a vital role in the topics like calculus, algebra, and many more. Okay, next we have questions in the examination from this topic are usually very direct. What it means? It means if we know our concepts right, then we can solve the questions in the examination very easily and fast as well. Okay, so the concepts are clear. It becomes high scoring chapter. Okay, next what we have is we will deal with types of relations like reflexive, symmetric, transitive, and all, and different types of functions, helping us to think logically, especially in the question. When we talk about questions, from the questions point of view, logical thinking is very much required to solve and break them easily and faster. Okay, so that is going to be a fundamental of this particular chapter. If you know the functions well, if you know the relations well. Okay, what it does is it uses graphs, arrow diagrams, and sets to learn the concepts inside this topic very easily. So you have applications of graphs, arrow diagrams, and set theory as well in this particular chapter. I hope this makes sense to you. So without taking any more of your time, let's start the chapter right away. So in the session outline, what we have is, so we're going to learn today in this particular session types of relations. Okay, so we have to see different types of relation which is there. For example, we have reflexive relation, we have transitive relation. Okay, we have symmetric relations, of course, and we have other definitions also that you have to involve there. Then next major part will be your number of relations. Okay, so first what we learned, so we learned our types of relations and their definitions, of course on the questions on them, and how to identify that, all the tricks that is required to solve the questions. We'll learn all of that. Then we'll move on to quickly learn one topic, which is number of relations. Yes, then there are less number of questions asked on this topic, but still relevant. Okay, so we'll solve that part as well. Next is questions practice. Of course, I've taken, even though it's a concept session, so we have still taken some questions over here, since this is a mathematics and you learn with the help of questions only. So some questions will also be practiced in the session itself. I hope this is very clear. Let's start with the session right now. So in this section, which is of types of relation of the chapter relation and function, so we'll learn about basically first definitions of different types of relation. For example, we have empty relations, we have universal relation, we have symmetric, transitive and reflexive relation, where the mostly questions are asked on. Okay, means the three that I said, symmetric, reflexive and transitive relation, questions are mostly framed on that only. But yes, even these are simple, yet sometime it might be useful for us in the when we talked about exam point of view. Otherwise, yes, questions are mostly asked in that section. We have seen that PYQs, you'll see that again in the sessions coming up for all of you. So this is a very important and very simple chapter for your PU2 syllabus point of view. Okay, why important? So because yes, 1 or 2 questions comes from this chapter, and simple because they have simply definition based questions. If you know them, you get the answer right away. Okay, so have a look. Empty or void relation is a relation where we talk about, of course, to define any relation we need a set. Okay, so let's say I've taken a set A, and any element of the set A cannot be related with any other element of the set A. When that happens, means there exists no element of the set A. Okay, for this there is a relation between, or that can be established between different element of the set A. For example, if I take over here, set A is defined like 1 2 3 4. Set A is 1 2 3 4. The elements are having there the total of 4 elements. So if you check this relation R, we talked about the ordered pair A comma B such that difference of A and B is 5. Difference of A and B is 5. Check here. Can you take any ordered pair? Can you take any ordered pair? Well, this relation is justified. Think about it. Can I take 1 2? If I take 1 2, so I get 1 minus 2. How much is this? Minus 1. If I take, let's say, another pair 2 3, I get again 2 minus 3. How much is this? Minus 1. If I take 1 4, let's say the biggest and the smallest and the largest value in this given set, if I take that 1 4, answer is again minus 3. So any value you take, any element you take in this given set A, there's no way you can define this. There is no way you can get this difference possible as 5. It means none of the element of the set A, okay, 1 2 3 4, is going to be related to the relation R. So this is called as empty relation. This is called as empty or simply void relation. Void relation. I hope this is clear. Very clear. Moving on. Now next we have universal relation. So just opposite to what we learned in the case of empty relation, here we'll talk about where each and every element of the set A will be related to every element in the set A. Yes, because if you're dividing, let's say, if you're defining the relation on the set A itself. Okay, this is not the set. Forgive me. 1 second. If I'm defining a relation R, okay, on the set A itself, then I'll talk about each and every element of the set A will be related to every element in the set A. Okay, so each element of the set A is related to every element of the set A. Okay, means R will be defined as simply A cross A. So for all the ordered pair possible for the, what is ordered pair? The Cartesian product of the sets, right? So if you take that, you get all the ordered pairs you get from set A to set A, those will be part of the relation R. Okay, think about it. So if I've taken the case over here as our set is defined as 1 2 3, set has 3 elements 1 2 3. Okay, then relation is defined like this: the modulus of the difference is always more than 0. Modulus of the difference is always more than or equal to 0. Think about it. Modulus means, this means a modulus, right? Modulus. And modulus means only positive values, only positive. Of course, other cases also there, or 0. Modulus means only positive or 0. It means if you take difference of anything, will always be more than 0, right? Or equal to 0. Means this statement for any element is there in the set A will be true. It means for all the elements 1 minus 2, which will be minus 1, take the mod, it becomes plus 1. Think about it. 1 minus 2 mod. How much is this 1, sir, which is more than 0? Take the biggest difference 1 and 3. I get here 1 minus 3. How much is this? Minus 2. Apply mod on this. Answer will be what, dear? 2, which is more than 0. So any difference, any ordered pair you take, 1 2 1 3 2 3 3 1, anything you take, always the difference modulus will always come out as more than 0. Worst case it can become 0. Think about it. 1 minus 1, how much is this? 0. Apply modulus on this. What is the answer? 0. 0 is what? Equal to 0. It can be what? Either greater than or equal to. It means for every element, each element in this set, the condition, the relation is defined correctly. Okay, this is called as a universal relation. It's called as a universal relation. I hope this is clear. Okay, so clearly all ordered pairs, if you check here, all ordered pairs means 8 1 2 1 3 2 3 3 1 2 1, all of these possibilities are defined properly, not a problem. Okay, so R is a universal relation on the set A, on the set A. Works. Moving on, next we have what? Next we have identity relation. So in this we talk about the elements of the set A will be defined, will be related to itself only. There's a word only over here, okay, not just itself, the word is itself only. You can see I have given a highlight over here, itself only. So any element, if I'm talking about from the set A, it has to be related to itself only. It means, let's say I have a set here 1 2 3, so I'll talk about 1 1 2 2 and 3 3. Means whatever the relation you write, it has to be for the ordered pair 1 1 2 2 and 3 3. Then only you can call this relation to be a identity relation, to be a identity relation. I hope this makes sense to you. Okay, moving on, reflexive relations. So now they are somewhat similar, but there's a difference. Most of the things of these two relations are similar only, but there's a difference. I'll write the relation over here and you get the sense of it. So let's write the relation. Okay, first ordered pair will be, of course, 1 1, of course 2 2, of course 3 3, and I'll write here 1 3. Think about it. Now this will be a reflexive relation. Difference, I hope you can see that. It means apart from the entity relation, there should be one element, or it can be. If I write, let's say, if I remove this 1 3 from here, I remove 1 3 from here and I ask you, is this reflexive? You'll say yes. If I ask you, is this reflexive? You'll say yes. Okay, but even if you write here 1 3 and I ask you, is this reflexive? Yes. Is it reflexive? Yes. Is it actually entity also? No. For entity relation, it has to be only to itself. Okay, only to itself means 1 1 should be there, 2 2 should be there, 3 3 should be there, and apart from that nothing else should come. Okay, whereas if you talk about reflexive, the understanding is minimum this should be there. Okay, entity should be there, and anything else comes after this. Even if it doesn't come, it's okay. But if something else comes after this 1 1 2 2 and 3 3, that also is allowed. Okay, so this is the difference between reflexive and entity relation. If I write another example, let's say I write here 1 1, let's say 2 3 3 3, and if I ask you whether this is a reflexive relation or not, on the set A, of course, on the set A, of course. Where is set A, sir? Set A is here. If I'm asking you, this is a relation, let's say relation R1, I'm asking you whether this relation R1 is reflexive or not. So answer will be what here? Not reflexive. Because yes, 1 1 is there, 3 3 is there, but there's 2 3, not a problem, but there's no 2 2. Means minimum of identity should be there. Means all reflexive relation will be an entity relation. I'll repeat myself. All reflexive relation will be an entity relation, but not ulta. Otherwise, not possible. The vice versa is not possible. Okay. So 1 1 1 3 3 is okay, but there's 2 2 missing. If I'm writing for the set A, I must have 2 2 over here. If it's not there, it means not reflexive. But for every element in the given set, there will be reflexive only possible if you have entity validated. If you have entity relation validated. Okay. Check here. 2 2 is missing. That's why not reflexive. So you should have 1 1 2 2 3 3. If that is enough, okay, that is also reflexive. Otherwise you can have other elements also, not a problem. But minimum 1 1 2 2 3 3 should be there. I hope we get the difference now between reflexive and identity. Okay, yeah, but they're similar somewhat, right? So there's no confusion about it, I hope. Okay, if there is, you let me know in the comment section. I'll cross verify it. Okay, we'll see, we'll have a discussion over there. Now let's start one more time. What is coming next now? Again, we have, as I said, 3 important relations are there where the question comes from is reflexive, symmetric and transitive. So second one is over here. Symmetric means, as the name suggests, if you have the ordered pair AB with you, let's say for any set A, you have 2 elements, A and B, okay? Then if you make an ordered pair out of it, you can make it like this. AB is our ordered pair. then if AB belongs to the relation R, if AB belongs to the relation R, then BA ordered pair should also belong to the relation R. Getting it? So let's say if I'm writing the relation R like this, okay, I have an ordered pair over here AB, okay, let's say I have here CA, okay, I have here BA, and I have here, let's say, something CD. This will be, sir, simply symmetric in nature. Reason is very simple. Please check over here. I have AB and I have BA. Okay, so what about, sir, CA and AC is not there? So CA is there but AC is not there. It doesn't work out like this in the case of symmetric. In reflexive, you have to check for all the elements. In reflexive, you have to check for all the elements whether the A and A should be there or not. Means in the reflexive, you write like this: ARA. So the ordered pair becomes here A comma A. So yes, you have to check the ordered pair for every element in the set. But in the case of symmetric, don't have to worry about all the elements. Only you check for if AB is there, you have to have BA. If you have AB, then you should have BA. Okay, then we'll call it symmetric. Okay, in this, like for example, over here, CA is there, then I should have AC. CD, let's say I don't have to. If I write like this, no, actually there's a change. If I write, let's say CA, okay, I wrote here it's CD, no, I have to remove this. You have to remove this. Then only I call symmetric. Otherwise, if I'm writing CA over here, excuse me, I must write here AC. So the symmetric relation is actually a conditional relation where you have if statement and then statement. You don't have to worry about all the elements in the set, but yes, if AB is there, then BA must be there. If AB is there, then BA must be there. Then only you can call the relation to be a symmetric relation. I made I made the change. I wrote here CD, right? It has to be AC actually. If it is CA, then it has to be AC over here for it to be symmetric relation. I hope this makes sense to you. Please check. I have over here, if 1 2 is there means 2 1 is there, 1 3 means 3 1 is there. Let's say even though I don't have the case of 2 3 or 3 2, you can think, sir, there is no 2 3, there is no 3 2. That's okay. If the first one AB is there, then BA is there. That's all we need. If you remember this much, that's good enough to solve any question from the symmetric relation. Okay, don't have to worry about what else is not there. Just worry about this is there means this should be there. I hope this is clear. Only the ordered pair relation is very important in this case. If and then statement for the ordered pair, AB, BA should be there. Works. How we write this? ARB is the if statement, and what is the then statement, sir? The then statement is given by BRA. This represents your ordered pair AB. This represents BA. ARB means ordered pair is AB. BRA means ordered pair is BA. I hope this is okay. This is clear. Simple, very simple. Okay, moving on. So anything else I've missed? No. Next is the last one, which is transitive relation. Okay, this is where student gets stuck in it. Okay, because then started very clearly, sir, very simple. You were writing here ARB, A, BRC. No, we'll write the same thing over here. Let's say we have A, RB. It represents the ordered pair of A comma B. Okay, so again we'll write here B, RC. Ordered pair is B comma C. This is again if statements. This also is a if and then statement question. Relation, sorry. So the condition is if you have ARB, means if the ordered pair exists, please check. If the ordered pair ARB exists, means A comma B exists. BRC means B comma C exists. Then statement is over here. Then statement is what here? Then statement is ARC. Basically it means A comma C ordered pair should exist. Means if in the relation R, I have here relation has AB in it, relation has BC in it, then I should have AC also in it. Then I should have AC also in it. Then only I can say this to be a transitive relation. Okay, so that's simple. Then why this student gets stuck into this? This is very simple, sir. A, B, B, C, then AC should be there. Simple to understand. Then why do students get stuck into it? Reason is, it's difficult to check for all the numbers possible. Let's say even for one number, one set of numbers, if it's possible to identify and say that it's not transitive, it means the whole relation will become not transitive. I'll repeat myself. If for, let's say for all, it says all real number. If you can figure out one set of all real numbers, any real number, let's say, of course you need three numbers, na? A, B, C. You have three numbers here, A, B, C. Okay. Let's say there's a relation defined on a set where the elements A, B, C are a real number. You are asked to find whether it is transitive or not. Okay. And you are not able to figure it out, but if you can, there's some way, you can give one number for which this is not transitive. You are thinking of, let's say, 10 numbers. All of them are transitive. coming out transitive. But even if there's a number which is giving me a result of not transitive, this whole relation will become not transitive. That's why it is difficult to check for all the numbers. So then what are you going to do? You have to remember some rules. If you remember that much, you will be able to solve most of the questions. When I say most, means more than 95% of the, not even 95%, 99% of the question can be solved with these, remember, simple rules. What is this? If you have, first of all, you have to check this is the first rule, okay? First rule is this, you have to check for this condition, AB, BC and AC. For whatever number you can check this rule. Otherwise, what is the second condition? This condition. Second rule, if you have AA and AB, no need to check. If you have BB and AB, if you have AA and AB or BB and AB, no need to check for transitive, it will always be transitive. No need to check, because it will always be transitive. It will be always transitive. Right here, always transitive. Excuse me. That's the condition. So first one is this definition of this relation, ARA, BRC, then ARC should be there. Second condition is this, if you have AA, AB, BB, AB, then no need to check, it's always transitive. And third condition, very important, okay, if we are not able to, basically, let's write a better statement, if we can't okay, I think word can't can be different now for different people, okay. So I'll say if there is no objections, actually, let's redefine the statement. It's very important to redefine properly. If there is no objections, okay, on transitive relation, then simply what will happen, you will define it to be always transitive. Now you might think, sir, how is this possible? It means that, sir, if your name is not Ankit, then you are not Ankit. That's how it means, right? If there is no objection on the transitive relation, it means it is simply a transitive relation. No objection means, of course, this should be a transitive relation. So you're saying that your name is not Ankit, means you're not Ankit. That doesn't make sense. Of course, it's understood only, but I'll tell you how it works. For example, let's say I'm writing a set over here, or writing a relation over here, relation R1 as 1, 1, okay, 1, 1, that's it. Will this be a reflexive relation? If it is, the set is only 1. If the set is only 1, will it be reflexive, sir? Yes. Okay, I forget about everything else. Can you check it for transitive relation? You can't check it. There's no way to check this relation as transitive. This will simply come out as transitive. Means there's no objection only. There's no way to object it. There's no way to give a restriction that it can't be transitive. There's no way possible to give an objection, to give a restriction on this relation R1 for it to be not transitive. In that case, what will happen? It will simply be called as a transitive relation. It will be called as a transitive relation, sir. That's simple. That's what it means. If there is no way to provide objections, okay, on transitive relation, then you can simply say that the relation is going to be transitive relation. I hope it makes sense to all of you. Okay, I know it might feel a little confusing to you, but it actually helps. When you see the questions coming your way, in the practice session or something else, I'll tell you this in the question that where this concept is applied. Okay, I'll take a question like this and explain it to you over there. Okay, in the practice session. Okay, today's session is mostly on the concept. That's why I'm not going to get into more of the question practice, but you have a practice session on the KCET, and then you're going to talk about your actual, very important objections, or the third point to find out or to figure out the transitive relation. Okay, works? Please check. This clear? Okay. Now the next one is the combination of all three. If you can say a given relation R is ARA, right? Remember this. What is this, sir? This represents ARA. So symmetric, sorry, reflexive. What is this, sir? AB, BA, symmetric. And what is this, sir? AB, BC and AC, right? So this is, sir, last one is transitive. So if a relation given to you is reflexive, is symmetric and transitive, then what are you going to call? You're going to call the given relation to be an equivalence relation. You're going to call this to be equivalence relation on the set A. You're going to call this to be equivalence relation on the set A. Okay. And how are you going to represent this? With a symbol this, also called as wiggle or a wave, which is used to identify a relation as equivalence relation. I hope this works out. Okay. Let's see a question on this. I hope this is clear. Simple thing. Combination of all the three is called as simply your equivalence relation. Now question 1 on this practice question. Let S be the set of all real numbers and R be a relation on S defined by A or B. Okay. The relation is what here? A square plus B square equals to 1. Let's check for reflexive first. So I'll check for the reflexive first. Have a look, reflexive relation. So for this, what is the ordered pair? We have A or A, right? Ordered pair will become A comma A. Use B as also A. You'll have over here A square plus A square becomes 1. Okay. So from here I'm getting what here? I'm getting this value as 2A square is 1. Okay. So from here I get A square is 1 by 2. A square is 1 by 2, which gives me two values over here. So A value becomes what? Plus minus 1 by root 2. Plus minus 1 by root 2. Okay. So we'll have over here, please check, A square plus A square equals to 1. Which is not possible, right? You can take a number A as 5. You'll get this square of 5 as 25 plus 25, which will never be equal to 1. So this is not reflexive, sir. Answer is what? Not reflexive in nature. Why I can take 5 and 5? Because we're defining on, please check, on the all real numbers, okay? Then sir, it will work 1 by root 2, 1 by root 2, or minus 1 by root 2, minus 1 by root 2. But you understand this, for all the elements in the set, the reflexive has to be defined. That's how we define the reflexive relation. Okay, for all the elements in the real numbers, okay, which is a very big set, it has to be defined. For example, you can check here any number you can take apart from 1 by root 2 and minus 1 by root 2. This will not work out. It means, of course, it will not be a reflexive relation. Not reflexive relation. What are we looking for now? Symmetric will be the symmetric. Yes. Please check symmetric relation now. For symmetric, I have what? I should have A or B. It means I can have what is it, sir? A square plus B square equals to 1. And if I take B or A, what I get? I get this time B square plus A square equals to 1. If this is true, this also has to be true. If A square plus B square is 1, it means even B square plus A square is 1. Of course, it means that symmetric relation R is over here, right? So relation R is symmetric relation. Now think about transitive, sir. What we have for transitive relation, the last part, C. For transitive relation, think what we have for this. Let's take a number 101. Okay, so if I take this 1 0 ordered pair, okay, and I take the ordered pair as 0 1, what am I getting? I'm getting over here 1 square plus 0. How much is this? 1. If I take 0 and 1, I get again 0 square plus 1 square. How much did I get? Again 1. But if I take the combination of first and last, which is 1 comma 1, I'll have the answer as 1 square plus 1 square, which is how much? 2, which is not equal to 1. It means I can think of an ordered pair. I can think of an ordered pair where it is not transitive. So understand this very clearly. In the case of reflexive, it has to be true for all the elements in the relation in the set S, which is the set of all real numbers. In case of symmetric, you have to think for only the pairs which is present. What is the pairs? The pair is A, B. It will be true for all the numbers because A square plus B square is same as B square plus A square. But in the case of transitive, I was able to create an objection. It will be more than this as well. You can think of other numbers also will be true in that case. It means that, so even transitive is not possible. Okay. So I get only condition is symmetric only our relation R is only symmetric. So option will be symmetric but neither reflexive or transitive. Option A is correct, right? Option A is correct. Please check. So it's symmetric but not reflexive, not transitive. I hope this is clear. Works? Alright. So let's move on now. Next is the number of relations, whether we'll talk about reflexive, symmetric, or the combination of both. So when we talk about reflexive relation with for the number of set, the cardinal number to be n, the cardinal number of the set, okay, then answer is given by 2 power n times of n minus 1. 2 power n times of n minus 1. This is for number of reflexive relation, whereas in the case of symmetric, you have n times of n plus 1 by 2. 2 power n times of n plus 1 by 2. Again, we will always have 2 power, okay? 2 power of n times of n plus 1 by 2. Over here we have 2 power n times of n minus 1. Whereas in the case of combination of reflexive and symmetric, combination of, so the cardinal number is m over here, and you have reflexive and symmetric relations. You're looking for the combination. Number of relations on a set with m number of elements which are both reflexive and symmetric. Answer is given by 2 power m times of m minus 1 by 2. Okay, 2 power m times of m minus 1 by 2. Yes, these questions on this are very rarely asked, but if they ask, can be worth 1 marks, of course. Then that's why it's good to remember the 3 basic formulas, of course. Let's move on. Yeah, now next question, question number 2. I have taken some questions, I don't want to just come in the session without any questions practice. So I have taken few questions, we'll practice that, and then we'll move on. We'll complete the session today, and then we'll move on to the, when we come to the practice session, we'll solve more and more questions in the practice session. Works out? Okay. Question number 2. For the set A, 1, 2, 3 is the element of the set A. Define a relation R on the set A as follows. Okay. R is 1, 1. 1, 1 is the first ordered pair. 2, 2 is there, 3, 3 is there, and 1, 3 is also there. They're saying what? How many ordered pairs to be added to R to make it smallest equivalence relation? Smallest equivalence relation. Of course, I can add more than, I can add multiple number of ordered pairs to get this relation R to be equivalence. There can be more than one way, but I'm looking for the smallest possible. Means the least number of ordered pair to be added to this. I'll repeat myself. The least number of ordered pair to be added to this to make this relation R to be equivalence. First of all, let's check whether it's equivalence right now or not. 1, 1, 2, 2, 3, 3 for the set A means, sir, reflexive. Yes, reflexive. Yes. Check for the symmetric now. Symmetric is it there, sir? 1, 1, 2, 2, 3, 3. Okay, 1, 3 means 3, 1 is missing. Okay. What about transitive, sir? So it is transitive only. No, please check. I told you whenever you have AA and AB, please check. This is your AA, and you have AB. Will you check for transitive? You will not check. It's always transitive. Okay, think about it. If you take here again, it will become what, dear? Combination of these two will become AB again. Okay, so whenever you have AA and AB, don't check, always transitive. So I have symmetric missing. So if I combine this set, this relation R with 3, 1, the ordered pair 3, 1, then it becomes what? Equivalence relation. So do one thing, add here 3, 1. Now check the modified relation R. I'm going to write this as R dash. Please check. Now in the R dash you have 1, 1, of course, 2, 2, 3, 3, 1, 3, and 3, 3. Now if you check again now, reflexive was there, symmetric, of course, 1, 3, and sorry, not 3, 3, right? 3, 1. I made a mistake. 3, 1. Symmetric now is there, and of course there was always transitive, right? 1, 3, 3, 1. It means the 1, 1 is there, which is all of course present over here. I told you if you have A, B, B, whatever it is, you don't check for A, B, B, A. Always transitive, sir. Okay. So answer is symmetric. Yes. So we need to add one ordered pair 3, 1 to make the relation R to R dash, which is this R is not equivalence relation, but this R dash is equivalence relation, and we have to add a odd what? We have to add only one ordered pair, which is 3, 1. The minimum number of ordered pair needed to be added to the relation R to make it, to convert this into equivalence relation is 1. We need to add only one ordered pair. We need to add only one ordered pair, which is 3, 1. Answer is what, dear? Answer is only one ordered pair, means option A. Option A. I hope this works out. Please check. I hope this is clear. Okay. Now have a look. Moving on. On the set N of all natural numbers, define the relation R by A R B if and only if the GCD of A and B is 2. GCD means greatest common divisor. Basically HCF, okay? Greatest common, doesn't look like it. 1 second, divisor, sir. 1 second. It means greatest common divisor. Okay, now it works. I hope the spelling is right. Okay, so I'm looking for the ordered pair, which is going to be what? Okay, have a look. Can I take reflexive? If I take number over here, it's defined on all natural numbers. Set of n, right, means all natural number. I can take 5 and 5, right? 5 comma 5 is a set of ordered pair for natural number, the relation, okay? So I can write 5 comma 5, okay? So GCD is what over here? 5, which is not equal to 2. It means reflexive not possible. Reflexive not possible. I'll repeat myself. Over here I can take ordered pair 5 comma 5 possible because it's part of the natural number set. Okay, for this ordered pair, what is the GCD, sir? GCD is 5. I'm saying that only has to be 2. Has to be only 2. GCD is 2. It means that relation R, this given relation R cannot be reflexive. So option A, part 1 we have discussed. Now part B, please check. Let's check the symmetric. Symmetric you want to check now. For the symmetric part, have a look. If you have AB, if the GCD, if AB GCD is 2, then of course for BA also will remain 2 only, no? Think about it. Think about it. If I have, let's say, 2 8, so if I take the ordered pair as 2 8, let's say 2 8, what is the GCD, sir? 2 in this case. If I take ordered pair as 8 2, I'll have GCD again as 2 only, na? The highest common divisor, basically HCF of 2 and 8 is 2. 8 and 2 is also 2 only, right? GCD means greatest common divisor, same as HCF. So HCF of 2 and 8 is 2. 8 and 2 is also 2. It means symmetric, yes. Transitive you check now. Transitive you check now. So if I take here C part, transitive, let me take a number, okay? 8 comma 2 as ordered pair. GCD over here, if you check, GCD is 2. Another one you're going to take 2 4, okay? GCD is again 2. Now last one will become 8 2 2 4, right? It will become 8 4. In this case, what is GCD? GCD is 4, sir. Okay, 8 2 GCD is 2, 2 4 GCD is 2, but 8 4, combination of these two, 8 and 4, it becomes 4. It means not transitive. So I have a relation R, okay, which is only symmetric, others two not possible. Okay, answer is B, only symmetric. I hope this is clear. I hope this is clear. Okay, if not, you let me know that as well in the comment section. I'll continue from here. Okay, let S be the set of all real numbers when the relation, okay, AB was defined like this. R equals to 1 plus AB is more than 0 means positive. So whether it is symmetric and all, we have to check for this. Let's take the first one, which is reflexive. Let's check for reflexive, right? Reflexive. So in this case we have to take ARA, right? The term for this ordered pair is going to be ARA, basically A comma A. Okay, if you use B in terms of A, you will have this as 1 plus A times of A. How much is that, dear? It's going to be what? Simply 1 plus A square. 1 is a positive number. A square is a positive number. It means the sum will always be a positive number. So yes, reflexive, possible. Reflexive, possible. Okay, so we can write here simply possible. Let's check for others. Other cases are symmetric. Okay, case B is, or second relation is symmetric. All right. For symmetric, you understand this. You have to take for ARB first. ARB means that 1 plus AB is positive. This is the if condition. If that is the case, it means that AB also has to be, sir, a number which is more than -1. More than -1, then only become positive, right? If I take, let's say, -2, it becomes 1 minus 2. How much is that? Negative. That is not true. That cannot be the case. AB has to be more than -1. Correct, na? In that case, what will happen, sir? Even BA will be more than -1. If AB is more than -1, then BA is also -1, more than -1, because product of two numbers is always same whether you multiply either in either order. You multiply 2 into -5 or -5 into 2. Answer is always -10, right? So you take AB, which is more than -1, even BA will be more than -1. In that case, what happens? I get this as moving 1 on this side. I end up with 1 plus BA is more than 0, which justifies the condition for BRA. This was ARB, this is BRA is also true. It means symmetric is also possible. I write over here as possible. Okay, so we have possible cases of reflexive and symmetric. Let's check the last one, which is transitive. Transitive. Okay, now think about a couple of numbers. Okay, so if I take numbers like, okay, let me take this, I'll try this. So minus 3, okay, minus 1 by 4 and 2. Okay, let's make the ordered pairs that we have. So minus 3 comma minus 1 by 4. For this you apply the relation. Okay, so I have over here 1 plus minus 3 times of minus 1 by 4. It will become, sir, 1 plus 3 by 4, which is of course more than 0. So this is not a problem. Please check over here. I have 1 plus minus 3 times of minus 1 by 4. It becomes 3 by 4, right? Which is more than 0. 1.75 will become more than 0 only, right? Yeah. Next one, I'm going to take this 2 together. So I have here next relation as r minus 1 by 4 and 2. I get this as 1 plus minus 1 by 4 times of 2. How much is this, sir? Please check. This will become, dear, 1 minus 1 by 2. How much is this? 1 by 2, which is more than 0. It means this ordered pair or this ordered pair, both are making positive results. Whether I take this first ordered pair or second ordered pair, both are making me positive result, not a problem. First one was 1.75, this second one is 0.5. Let's take the last one, which is what? Minus 3 and 2. Minus 3 and 2. So for this, what I get? I end up with 1 plus minus 3 times of 2. How much is this? 1 minus 6. And how much is this, sir? It's going to be minus, excuse me, going to be, 1 second. Okay, I think, yeah. So let me write it over here. It's going to be, if I erase this, 1 second, I'll take the eraser over here. Okay, now let me write it. Okay, so 1 minus 6 will become what? It will become minus 5, which is not more than 0. Not more than 0. Please check. I'm getting here 1 minus 6, right? Which becomes minus 5, which is not more than 0. It means your ARB was true. BRA was true, but, sorry, not BRA. ARC, na? BRC over here, excuse me. BRC was true, but ARC is not true. It means not possible for this statement. Not possible, sir. Okay, not possible. It means not transitive. Option is, please check. We have symmetric and transitive, but no. The case will be option A, right? Reflexive, symmetric, but not transitive. Option A is correct. Have a look. Reflexive, possible. Symmetric, possible, but transitive, not possible. I just concluded with the help of 3 numbers, minus 3, minus 1 by 4 and 2, which are all real numbers. I hope this makes sense to all of you. I hope this is all visible to you. Okay. Download the class notes. Of course, you know the access to the class notes. What is this? You have to join the WhatsApp channel. There only you're gonna get the access of all the class notes. Okay. So in the PDF format you're gonna get, you can access and download from there. You have to join it right away if you are new to the platform of Diksha Karnataka. If you're not new, of course you know where to get the sessions PDF. Okay. Very important to do that. Let's move on now. Next, this is clear. Next is what, dear? Next is, for any two real numbers, A and B, we define ARB if only if, okay, this is the relation for us. The relation is given like this: sin square A plus cos square B equals to 1. I have to check for same thing, reflexive, symmetric and transitive. Okay, so all right, I can apply the ordered pair condition AA, AB, BA and all. But I can do one thing over here. I can rewrite this relation in this form. I'll have over here as cos square B equals to 1 minus sin square A, which gives me cos square A. This is cos square B, right? Okay, cos square B and cos square A. Now, this is okay, I guess. Yeah. Now do one thing. Let's apply one by one all the 3 we have over here. First one is reflexive, right? Okay, first one is reflexive. Now if you check over here, ordered pair will become what, dear? It will become A comma A, right? Because this is going to be ARA, no? Yeah. So this is given by what? If you check over here, of course it's going to be true. Cos square A equals to cos square A. No arguments there. Cos square A is of course going to be equal to cos square of A, because B becomes A in this case. So of course no argument over here. So reflexive, yes, possible. Possible, sir. Okay. Let me simplify this and write it as yes only. Reflexive, yes. Reflexive, yes sir. What about this next one? Symmetric. Okay, we'll check this part as well. So let's write here the ordered pairs. We have A, R, B should be there. It means ordered pair is A comma B. It means what, dear? It means that this is if condition. Okay, this is if condition. Okay, it says cos square B equals to cos square A. They've given that cos square B equals to cos square A. They've given this already. Means this, I think that this is true statement. Now check the then statement. Of course, what is going to be this? BRA. What it means simply, dear? It means this to be ordered pair is BA. Reverse it. It becomes what? It becomes cos square A in this time equals to cos square B. Of course, this is true. Whether you write this over here or this over here doesn't matter, right? So square B, cos square of B equals to cos square A means cos square of A equals to cos square B. In that case, this also is yes. Symmetric also is yes. Last one, transitive. Last one is transitive. Please check carefully. Now for this end, for transitive relation, what we'll have? So we'll have here, let's say, I have here A, R, B if I'm writing. I'll write directly over here. A, R, B if I'm writing. A, R, B, it means cos square B equals to cos square A. Then we write here now BRC. BRC means cos square C equals to cos square B. If you combine these two together, check here, cos square B and cos square B. It means cos square A equals to cos square of C. Cos square of A equals to cos square of C. From here I can imply that even AC works. Even AC works, okay? The relation on AC also works. In that case I can say that the relation is, this also is yes. So the given relation is yes, it is a reflexive relation, yes, it's a symmetric relation, and yes, it is a transitive relation. It means the conclusion is going to be true for all the three, hence it's going to be what, sir? An equivalence relation. And equivalence relation. Option D is correct. Have a look. Option D is correct. I hope this makes sense to you. Makes sense? Pakka? Okay, so this completes our session today. Yes, I've taken very less amount of questions, but that's all right, sir. Reason is very simple, because the session was only for concept part, so we have done that today. And in the next session, after all the concept of this chapter is over, chapter is relation and function. Once that all of that is over, we'll move on to question practice as well. Okay, so I hope you enjoyed the session. I hope you liked it. Any feedback you have, anything you want to tell me, let me know. Leave that in the comment section of this particular video. I'll get back to you with a proper reply in a very less time. Till then, you have to again wait for the next session of mathematics. Other session also going on. Till then, of course, you have to wait for some time, and I'll be back again in the next session. Till then, take care. Bye bye.